It's over here. 1 second. Calculator. I'm going to have my periodic table as well. I'll tell you why I'm going to have my periodic table once we get there. So in the 8-2 discussion packet, part A, I think you can answer based on your 8-1 packet, right? Going down, what does STP stand for? We've been looking at a lot of these things already. We talked about the ideal gas law yesterday, right? PV equals nRT. We'll hit on these again. We will also hit on the values of R once we look at the practice. So if we go to number, here we go, 11, all right, our first starred question. Number 11. If the pressure, now as I go through, I'm going to try to do my labeling of everything. So if the pressure of a gas at 297 Kelvin, so Kelvin measures temperature, in a volume of 0.044 liters is 3.81 ATM. So I have temperature, I have volume, I have pressure. How many moles are present? Now the first thing with this, notice I have one of each variable. I have P, V, T, I'm solving for N. We're going to use the ideal gas law. So ideal gas law, I'm going to write out over here first. PV equals nRT, right? Pivner, that's the ideal gas law. With each of these, I'm going to kind of label everything over here, all of our units that we should have so we make sure that we're good before we plug in. Pressure should be in ATM. Volume should be in liters. N is number of moles. And remember, temperature in any gas law problem has to be Kelvin. We have to use absolute temperature because there's no negatives. Now, R is the ideal gas law constant. We are typically going to use the value of R that works in atmospheres. I will always give you the value of R that's in atmospheres. So if you have a pressure and it's not in ATM, if you don't want to memorize the other values of R, just convert your pressure to ATM. R is 0.08206. That's a constant. The units are liters times ATM over moles times Kelvin. So to use that value of R, it tells you your units you need for everything else. Liters, ATM, moles, and Kelvin. So we're going to go through and practice some of these conversions. How do we go from milliliters to liters? How do we go from grams to moles? All right, what if our pressure needs converted? So this tells us what we need for the ideal gas law. Now if I look at everything up here, temperature is in Kelvin, volume is in liters, pressure is in ATM, I'm solving for moles. I will show you what I've had some people do before. They like doing this just so they can kind of see all their variables, is they'll actually go down the side. So pressure, 3.81 ATM, volume, 0.044 liters, N is what I'm solving for, and temperature is 297 Kelvin. Now the reason that I'm showing you this is because some people like to do this, just so now they can look and see, is pressure in ATM? Is volume in liters? Is temperature in Kelvin? Yeah, right, all of our variables are good. So now we can use the ideal gas law. Now with the ideal gas law, I like rearranging first so that you're not trying to plug everything in and then rearrange the equation. My goal is to solve for N. Be careful with manipulating equations. The goal is to solve for N, which means I want to get N on a side by itself. So I need to get rid of R and T. If we're multiplying R and T with N, how do we get rid of multiplication? Right? Divide both sides by R and T. So I'm going to divide PV by R times T. When I divide nRT divided by R and T, it cancels out. So notice how it's N equals PV over RT. Right? N equals P times V over R times T. Be careful with your algebra. Now I'll plug the numbers in. We've already checked to make sure our units are correct in what they need to be to plug in, so I'm just going to plug the numbers in. I'm going to put the top in parentheses and the bottom in parentheses just to help when we plug in the calculator. So pressure is 3.81 ATM times volume, 0.044 liters, divided by R is always this constant, 0.08206, and then temperature, 297 Kelvin. I didn't show the units here just to save some space, but all of our units will have canceled except for moles. Now to plug in, I'm going to plug it in just like this. So I'm going to plug in using parentheses, 3.81 times 0.044. Notice I put the top in parentheses. I'm going to do divided by, and I'm going to use parentheses again, 0.08206 times 297. So notice how I plug this in to the calculator, 0.006878. Let's say we round to 3 significant figures. Right? 3 sig figs is not necessarily 3 decimal places. Leading zeros are never significant. So 1, 2, 3. I'm going to round to this 7. Does this stay a 7 or move to an 8? Move to an 8, right? Because look at what comes next. So N is 0.00688, and our unit for N is moles. So that's using the ideal gas law. The purpose of using the ideal gas law is that if we assume that gases behave in an ideal manner, which is definitely an assumption to make, especially in a room like this, but if we assume that gases behave ideally, the ideal gas law allows us to calculate for any of these variables. R is always a constant. Now let's look at number 12. So 12 says, what is the pressure? So what is the pressure? That's what I'm solving for. So I'm going to put a P on top. I'm going to label my variables. Of a gas if a 3.4 liter container. Liters measures what variable? Which of the variables in the ideal gas law? Volume. Contains 48 grams of oxygen gas at 47 degrees Celsius. I'm going to skip 48 grams for now because grams isn't in the ideal gas law. It says at 47 degrees Celsius. There's my temperature, but remember, as soon as I see degrees Celsius, I'm going to make myself a note to convert to Kelvin. Then it says, remember, the amount of gas has to be in moles, and the temperature must be in Kelvin. So I gave you a little hint there. This 48 grams is how I will eventually get to moles. Now that's not my moles. I put an arrow because I need to convert to moles. So I know I'm solving for pressure. I'm going to go through what I did up here, and I'm going to label my variables, and then we'll convert as we need to. So down the side over here, pressure, volume, number of moles, and temperature. I'm going to label all of my variables here. Pressure is what I'm solving for. I'm going to put a question mark. Notice I didn't write R because R is a constant. R is always the same thing. Volume is 3.4 liters. Now it tells me this little hint here. Remember, the amount of gas has to be in moles. So they gave me 48 grams of oxygen gas. Oxygen gas, so we're going to go back and we're going to be reviewing things that we've talked about all year. Oxygen gas is unique because when oxygen is by itself, it's O2. So we will use that to get to moles, and then temperature is 47 degrees Celsius. I know I'm going to have to convert that as well. So I'm going to put stars next to N and T because I need to convert those. Pressure I'm solving for, volume is in liters already, N and T are going to have to be converted. I'm going to convert temperature first. You're always going to be given the conversion between Celsius and Kelvin. Remember, K equals C plus 273. So 47 plus 273 is 320 Kelvin. So there's my temperature. Now, my amount of gas right now is in grams. I need to get that to moles. I'm going to show it up here just so that you can see my work a little bit better, so I'm not trying to squeeze it in. I have 48 grams of O2. The reason it's O2 is because it's oxygen gas. When oxygen exists on its own, it's one of the 7 diatomic molecules. I want to go from grams of O2 to moles of O2. Can I go from grams to moles all at once? Yeah. Remember, we have our grams to moles to particles conversion. I can go directly from grams to moles. The mass of 1 mole comes from the periodic table. All right, it's our molar mass. I'll show you my periodic table so that we can look. This is just 1 O. So then what's O2? 32, right? 16 times 2. 32 grams. So again, you're looking at this, you're saying, why do I have to convert? To plug into the ideal gas law, the amount of gas must always be in moles. N is moles. So 48 divided by 32, because it's 48 times 1, divide by what's on the bottom, 1.5 moles. So now here, I'm going to put an arrow, 1.5 moles of O2. So now we've converted our grams to moles, our temperature is in Kelvin, our volume is in liters. So now I'm going to look at the ideal gas law. PV equals nRT. My goal is to solve for pressure, so I need pressure on a side by itself. How do I get pressure on a side by itself? How do I get rid of the V here? Divide, right? Divide both sides by V. When I divide both sides by V, that gets rid of the V. Gets rid of the V here. So I get pressure equals nRT over V. Now plug in. So N is 1.5 moles. R is always the same, 0.08206. That's a constant. Temperature is 320 Kelvin divided by the volume, 3.4 liters. If you say, why do we have to make sure that all of those units have, or all of those variables have the correct unit? It's because of the units of R. Our units of R are liters, ATM, moles, and Kelvin. So then we plug this in. Right, 1.5, nope, not 15. 1.5 times 0.08206 times 320, and I'm going to divide by what's on the bottom, which is 3.4. Say I round to 3 significant figures again. 1 is significant, 1 is significant, this 5 is significant. So I'm going to round to this first decimal place. Does this stay a 5 or move up to a 6? Moves up to a 6. So we get 11.6. Pressure is what we were solving for. Looking at your value of R, pressure is ATM. So 11.6 ATM. Now I think what we'll do is actually switch over to part E. So we were in part B just doing those practice questions, and I think what we're going to do just to kind of wrap up the ideal gas law stuff for today is we're going to actually look on part E, so bottom of page 3, and we're just going to review the ideal gas law. So we'll look at number 8, 9, and 10. So with number 8, what's the ideal gas law? So again, I'm trying to make sure that we review this equation as much as we can. So what's the ideal gas law? PV equals nRT. Here people say Pivner. Again, this is at the bottom of page 3 on part E. Right, bottom of page 3 on part E. PV equals nRT. Now it says label each variable. So we're reviewing lots of ideal gas law today. P is pressure. Pressure should be in ATM. V is volume. Volume should be in liters. N is number of moles, which unit is moles. And then T is temperature in Kelvin. R is the ideal gas law constant. Right? R is ideal gas law constant, meaning it's the same. You can use different values of R based on the units that you're working with. The R that I will always give you, though, so move over here, the R that I will always give you is 0.08206. Units, liters times ATM over moles times Kelvin. This is the value of R that I'll give you all the time. There are other values of R. So another value of R that you might see is 8.314. That's if your pressure's in kPa. Notice the only difference there is pressure's in kPa instead of ATM. All of the other units are the same. So you could use a different value of R. You would have to memorize them though. I will just give you 0.08206. So if pressure's in anything else, you could easily convert it. So let's look at question 9. Again, just to review what we've done so far. So calculate the volume. So we'll go through and we'll label the variables and then see if you can solve it. Calculate the volume that a 0.323 mole sample of gas will occupy at 265 Kelvin and 0.9 ATM. I'm going to look at each one of these variables. Is pressure in ATM? Yes. Volume I'm solving for is the amount of gas already in moles. Yes. R is a constant. Is temperature in Kelvin? Yeah. So I'm going to just write the ideal gas law, and then I'm going to solve. So PV equals nRT. My goal is to solve for volume. Make sure you can manipulate equations. I want to get V by itself. I want to get V by itself. I'll divide both sides by pressure. So volume equals nRT over P. Now I want you to plug all of your values in. Solve for V. I'm going to plug the units in so you can see how they cancel. You don't have to, but look at what your unit for volume would be. So plug all of your numbers in. So 0.323 moles, 0.08206 liters times ATM, moles times Kelvin, 265 Kelvin, and 0.9 ATM. So I'm just showing how the units cancel. You have atmospheres on top, atmospheres on bottom. That cancels. Kelvin will cancel with the per Kelvin in R, and moles will cancel with the per moles in the R. The only thing that we are left with is liters, which is why when we plug in and we solve for volume in the ideal gas law, we get liters. So if I look at plugging everything in here, 0.323 times 0.08206 times 265, I'm going to divide by 0.9. I get 7.80. Now again, look at what your units for volume are. Volume is liters. So the last question, I want you to see if you can try number 10. All right, see if you can try number 10. What is the pressure in ATM of a 0.10 mole sample of helium gas at 20 degrees Celsius if its volume is 0.505 liters? Pay attention. First thing you should always look at are all of your units for your different variables. So see if you can solve, convert whatever needs to be converted, and solve for pressure. One thing you should make sure to convert is temperature. And then to get pressure by itself, it's nRT over V. Divided by 0.505. Should get 5.14, but all of your answers should always have units. Solving for pressure out of the ideal gas law will be an ATM. So a lot of today was reviewing the ideal gas law, units to make sure to have, how to manipulate. What we'll look at tomorrow, we'll look at Dalton's law of partial pressure. We'll look at STP. STP just gives us another conversion. But make sure that you have, for like conceptual stuff in parts A through D, make sure you have that done. So if you look at, right, I know like part C, we didn't do the two starred ones yet. We'll do those tomorrow. I will tell you though, like number 15, the relationship, we did that in the do now. That's molar volume. That's this. 1 mole is 22.4 liters. Part D, Dalton's law of partial pressures. We did that in the do now. So just using that, we have the discussion check tomorrow, and then we'll finish up these starred questions, more of part E to review, and then you'll be able to work with groups. So we'll continue this tomorrow, but at least we were able to focus on the ideal gas law part of it today.